So welcome back. Your Today we're going to be talking about the EAN rule, which is known as the effective atomic number rule, or the 18 what electron rule. So when we talk about the 18 electron rule or effective atomic number rule, it is based on the stability and how we calculate the stability of organometallic compounds. That is when we talk about the stability of what organometallic compounds. So this rule is based on that stable organometallic compound should have 18 electrons. So the rule is just based on that is stable organometallic compound should have 18 electrons in their atomos shells. So like that of the noble gases, the likes of the noble gases that we say they must have 18 electron for them to be they should have 8 electrons for them to be chemically stable. So likewise the organometallic compound, so we classify their stability based on their numbers of electrons, which the maximum they can add is what is 8n, which is to classify them as being stable. They are said to be what they must attain 18 electrons. So now this rule was first proposed by Sedgwick. So the rule was first proposed by Sedgwick and later extended by Bailey. So it was later extended by Bailey. So Sedgwick was the first person to propose the effective atomic number or the late 18 electron rule, which was later extended by Bailey. Therefore, it is also referred to as Sedgwick Bailey rule. So it can also be known as Sedgwick Bailey rule because the two are said to be the pioneer of the 18 electron rule. Although there are many exceptions to this rule, it still provides useful guide to the chemistry of many organometallic complex. So now the 18 electrons in the valence shell of the metal will occupy our s electrons, the p and the d orbital, a total of 9 orbitals which can accommodate 2 electrons each, giving a total of what 18 electrons for a complete shell. So now this makes an organometallic complex to be kinetically stable. So by this definition, the metal should be a transition metal and must be greater than 4. So when we talk about the organometallic, for we to attain 18 electrons, the metal in consideration should be what a transition what metal. So if there are less than 18 electrons in the valence shell of the metal, an empty low lying orbitals into which electrons may be promoted will be available. So now this will lead to a decomposition or slightly heating. That's why. So when an element fails to attain stability by having 18 electrons, so that is it will say to decompose on any slight heating. So that's the consequence when they are said to when they are not stable. So that is we say that organometallic complex is said to be stable when it attains 18 electron rule. So when it does not attain, so it is prone to what decomposition on slight heating. So and also if there are more than 18 electrons, that is the other one we talk about, when there are less than 18 electrons, they are prone to decomposition or slight heating. And now if there are more than 18 electrons, the excess electron will move to the anti-bonding orbitals, which will reduce the stability by decreasing the bond order due to the interaction with bonding what electrons. So now we will talk about the applications. What are the applications of the 18 electrons? So now what are the what applications and how it's been what calculated? Talking about the application and how it's been calculated. So now the 18 electron rule helps to predict. It helps to one of the application is what stability. So it helps to what? Predict stability of organometallic complexes, and also helps to predict the most probable structure of newly synthesized organometallic complexes. You can say the first one is what? Is to predict what? Stability, that is how stable a newly synthesized organometallic complex will be. That is, we need to predict. So that's it. We have different kinds of compound, that is, they are said to be what? And you have different kind of compound. Some are stable, while some are what? Are not stable. When we talk about stability, that is how stable, how resistant are they to some certain conditions, like it's on when an organic complex is said to be not stable. One of the consequences is that unlikely it to decompose. So there are some so when you see something is said to be stable, that is, it can withstand some phenomenon. So that's it. So the help of 18 electron rule is to predict the stability of what? Organometallic complexes, and also helps to predict the most probably structure. Two is what? Predict structure. So it helps to predict the most probably structure. So that's one of number two. It predicts the most probably structure of newly synthesized organometallic complexes. Give us a probably structure. So that's one of the two most important application of the 18 electron rule. So the application of the 18 electron rules involves the determination of electrons in the valence shell of the what? Of the metal. So now, when we talk about the 18 electron rule, there are two phenomena. So when we talk about the 18 electron, we make use of we make use of transition metal compounds. So now, and there are two methods for the 18 electron rule. We have two typical method for the used to calculate the 18 electron rule. So the first method here is the neutral method. So that's the first method, is the neutral method. While the second one is what? Is oxidation state method. So the second one is the oxidation what? State what? Method. So now when we talk about the neutral method, so in this case the metal has a zero oxidation state. So that is, there are what? A zero oxidation state. And don't forget, when we talk about a oxidation number or coordination complexes, so that is, we have both our Lewis base and our Lewis acid. So now in our organometallic complex compounds, we have our transition metal, which is what? Associated to what? To some ligands. So that in this scenario, the transition metal will carry zero oxidation state, while the ligands will be what? Said to be neutral. When we talk about the ligands being neutral, that is, they will carry their usual charges. So that is, they will carry their what? Their usual charges. So now, those are the two phenomena. In the next step, which is the oxidation state method. So now, when you talk about the oxidation state method, that is, the first step is what? Is to know the oxidation number of the transition metal, and then calculate for the respective ligands. So now, one of the most prominent and effective method which we would emphasize here is the neutral method. That is, we will make use of the neutral method in calculating the 18 electron rule. So we've emphasized on the neutral method. So now, as we've said earlier, that is, the neutral method is based on when the metal has a zero oxidation state. So now, let me just give you a clue on the neutral method where they have their zero oxidation state. So there's a phenomenon here. So we have to know we have three. So make use of their valence electron. So now for scandium and yttrium, they have three valence electron. For four, those that has four, we have the titanium and yttrium. Then the next one, for five, We have the vanadium, we have the NB. So this is just a trick. So to save yourself the stress, so you can easily know their valence electrode to calculate your 18 electrode. For the 6, we have the chromium, we have MO, we have the tungsten. So also for 7, we have the manganese, TC, we have RE. So also we have our iron for group 8. We have our ruthenium, we have our osmium. So we have our cobalt for 9. Our Irish iron. And for 10, we have our nickel. We have RD and PT, platinum. So for 11, we have copper, AG and AU. We have our copper, silver and gold. So this is one of the tricks for recognizing. So the first one is when we talk about the zero oxidation state, we make use of their valence electron. So this is one of the first method in our zero oxidation state in our neutral method. So that is where all respective metal has a what? A zero oxidation state. So that wherever you have scandium using of our neutral method, so the valence electron for scandium should be 3, and for our titanium should be 4, vanadium should be 5, chromium should be 6, manganese should be 7, our iron should be 8, our copper should be 9, our nickel should be 10, our copper should be what? 11. So this is one of the first step. So the next one is how to what? Calculate. So the next one is how to what? Calculate. So now before we move to that, we should also know our ligand chart. That is our ligand, the charge and their respective charge. So now when we have the likes of hydrogen, our halogens, so they mostly have 1. So their charge is always +1. So likewise when we have their charge is always 1. Likewise when we have our OH group, our hydroxy group, is always also 1. And also when we have our OH or OR, when we also have our cyanide CN, there it is also what? 1. And we can have our alkene part, which is also 1, our NO. Now we have kinds of NO. We have the bent and the linear. So the bent is also 1, while the linear is 3. So we also have our CO. So our CO and P R3 is said to be 2. So that one is said to be what? Is said to be 2. And also our ammonia, NH3 and H2 is also said to be 2. And like our carbene, our ethylene, they are said to be 2. So then when you talk about also our halide is said to be 3. Our carbene is said to be 3. Ethylene diamine is said to be En, which is said to be 4. Our pyridine is said to be 4. Our butadiene is also said to be 4. But our cyclopentadiene is said to be 5. Our benzene is said to be 6. And cycloheptatriene is said to be what? 7. So these are one of the clues in calculating our 18 electron. So you go into a specific what? Example. So moving to a specific example. So now the first example before us is this. So we have our Fe surrounded with our cobalt. You can see we have our cobalt, so you can see This is, what is the name of this compound? This is FeCO5. So now our question here is to what? Is to predict the stability of this organometallic complex. So this is iron pentacarbonate. You can see this is iron pentacarbonate. So now we need to check if this compound is said to be what? Is said to be stable. That is, if it obeys the 18 electron rule. So now, don't forget, you make use of the neutral method where we say the transition metal has a zero oxidation state. Now, the transition metal here we have is Fe. So that is with zero oxidation state. So with zero oxidation state. So now the valence electron, as we always stated here in our previous slides, the valence electron of iron here should be what? Should be D8. Should be 8. So the valence electron is what? Is D8. So now our electrons here should be 8. So you have 8 electrons in the valence electrons. So the next step is to consider the ligands we have. So we have 1, 2, 3, 4, 5. So we only have only carbonyl group Cu. That is, we have 5 carbonyl groups surrounding it. So we already know the charge. The charge of carbonyl is 2. So we can see. So we have 2 electrons. We have 2 electrons for our carbonyl. So now the total numbers of electrons here is what? Is said to be what? 18 electrons. We can see our iron pentacarbonate obeys the what? 18 electron rule, which is so that this means that iron pentacarbonate is said to be what? Chemically stable. You can see it's said to be what? Chemically what? Stable. So it does not decompose with slight heating. So it's said to be very stable. So let's consider other respective what? Examples. We need to consider other respective examples. So let's consider some respective examples. So the next one we have here is this. So don't forget, when we talk about our in the terms of coordination complex, so to represent compound, we put them in a bracket. That is to show it is a complex. We put them in a bracket, CO2. So now we have titanium here as the transition metal, and we have Cp. Don't forget, when we talk about Cp, this is we have Cp 2Cp2. That is, our Cp is an acronym for cyclopentadiene. So this is we have 2 cyclopentadiene, and we have a what? A chlorine, 2 chlorine. So that is, you may have to give her the structure. Now to give her the structure, we have Ti, our titanium, and our Cp. So this is our Cp. Don't forget, is our cyclopentadiene. We have 2 Cp. I think you are cool with the class. So any question should be dropped in the comment section. So you can see this is the structure. So we have our Cp. So we have our organometallic complex. So now the next thing is to calculate for the oxidation state. We are told to calculate for the what? Oxidation state. So now the first one is titanium. The first one is to what? Is to go for our what? Our titanium. So we have titanium to be Ti. That is, just say it is what? Plus 4. You can see titanium to be what? To be plus 4. So this is titanium. So now the number of this structure is said to be bis aptic 5 cyclopentadiene dichlorotitanium 2. So this is said to be what? titanium what 2. So the next step is that to calculate the EAN. So we have titanium 2. So now the numbers of electron here is 2E, that is 2 electrons, and we have 2 CP. We already know that CP is 5, which is a ligand. So that is 2 times 5, that is 10 electrons. So we also have our chlorine, which is, we have our chlorine also, which is 2 chlorine. We have chlorine, which is 2. So you have 2Cl. So this sum it up to 4 electrons. So you have 2Cl, which sum it up to 4. So our total electron here should be what? Is 16 what? Electrons. So this is for our base activity of 5 cyclopentadienyl dichlorotitanium 2. So now the next one we also need to consider is, the next one we would consider is, let's consider this. You have manganese. We can consider this one. So this is the name. We have Mn2. So this is our structure. So we can see we have 2 manganese. We can just decide to pick one. So in 0 oxidation state, using our normal 0 oxidation state, so we have 7 electrons here. We already know magnesium, the valence electron is what? Is 7. So since we can just pick one out of the, we can just decide to pick one. So since we can balance it up, we can just decide to pick one. So we have 5 each. We can make 5 carbonyl here, so which is 10 electrons, and also we have 1 electrons in the complex. There is a presence of 1 electrons in the complex. So due to Mn manganese bond, so we have 1 electrons in the complex. So which gives us what? A total of what? 18 electron. We can see this is said to obey the 18 electron rule. So I think we are cool with this. So now I'll give you some quick examples for you to try. So there'll be a quick quiz for you to try. So we have this. So this is a quick example here. So now this is quite and very simple. We can see here, with the first one here, we have the apticity is 5. And we have our transition metal, which is what? Our iron, surrounded by your 2 carbonyl and our chlorine. So to calculate this using the neutral method, that is our 0 oxidation state. So you have iron at 0 oxidation state. So the valence electron is what? Is said to be what? 8 electrons. We have just 1 CP, that is 1 CP here. So that's said to be what? 5 electrons. So the next one we have is we have carbonite, which is 2. We have 2 carbonite. So the charge of carbonite is said to be 2. So that is 2 times 2, that is 4 electrons. So then we just have one chlorine group. So one chlorine. So the charge of chlorine is said to be 1. So that is 1 electron. So the total electron is what? 18 electrons, we can see. So that's quite simple. So now the next one is we need to talk about the limitations of effective atomic number. What are the limitations? So every single stuff in chemistry has their own what limitations. So now the limitations of the effective atomic number. So the limitation of 18 electron rule. So there are no known cases in which the metal center in organometallic compounds do not have 18 electrons in their valence shell, and they are very what? Stable. That is, there are some organometallic compounds that do not have 18 electrons in their valence shell, and they are said to be what? Very stable. So example is this, which is 8, and we also have this, which is 12, and we also have this, which is 16. So this is the limitation. It is not every organometallic complexes that has 18 that obeys the 18 electron rules, and so some do not obey the 18 electron rule, but they are said to be what? To be stable. So that's it. So the geometry adopted by this complexes is square planar. So the bulkiness of bonded ligands impose steric effect on the approaching of incoming ligands. So this can also impose limitation with regards to the number of what ligands that can be accommodated by the metal and the number of electrons in the valence shell. So that's a very good example. That's one of the great limitations to organometallic to the 18 electron rules. That is, not everything obeys this rule. So not all what obeys it. So those are the limitations. So we can try some more and respective examples. So we can try some respective example under the 18 electron rule, so which will guide us more. So I think this is the end of our class on the 18 electron rule. So we can work more on it privately. So make sure to subscribe and follow our YouTube channel. So thank you very much.